Okay, thank you, Mattia. The topic of my talk is experimental optical phase measurement at the exact Heisenberg limit. And as you see, because there are a number of authors on this work, which are indicated in this with a variety of different textual styles. So let me explain what they are. So all the authors in red are at my center, the Center for Quantum Dynamics in Griffith University, and part of the Center for Quantum Computation and Communication Technology as well. The authors who are in bold are theorists, and the authors who are underlined are experimentalists. And I should say, so the author who's not in red, that's Dominic Berry, is the Department of Physics and Astronomy at Macquarie University. So you'll note that there's one author who's actually both in bold and underlined. That's the first author, Shakib Daryanoush, who was my PhD student, who started doing the theory for this work, and then decided that given that he'd done the theory, he really wanted to see the experiment done as well. And so halfway through his PhD, he changed to doing an experimental PhD with Jeff Pryde, who's a professor in the center. And so, so he did both a lot of the detailed theory about the final experiment I'll be talking about here, as well as leading the experiment. Okay. And funnily enough, he's now also at Macquarie University, but anyway. All right, so before I actually begin the talk, I want to put up an advertisement for two posters from members of my group who are here. So on Thursday, Arya Chantasri, Sans Koala, will be giving a talk on quantum state smoothing. So this is related to what Klaus talked about earlier today. So to do with correlation functions and backwards in time things. So yes, you can go along and see that on Thursday. Today, there's Gerardo Paz Silva, who will be talking about open quantum systems, or modeling open quantum systems with arbitrary initial conditions. So yes, come along and see him. And so so this incredibly cool guy, I put him second because I also want to, as well as advertising for two posters, I want to put up an advertisement for two postdocs. And so Gerardo and I have money for two postdocs in quantum control, and so this seemed like a unique opportunity to be able to advertise these postdocs at a conference like this. So it's so-called OSMURI funded, which means that it's an Australian and US collaboration. And so in Australia, as well as us at Griffith University, there's Andrea Morello at the University of Sydney doing experiments in solid state, and Chris Ferry at UTS, also in Sydney, who's an expert in machine learning. And so so if these sorts of things sound interesting to you, and if you'd like to cuddle a koala, then maybe you'd like to come and work for us in Brisbane in Australia. So there'll be two positions, as I said, one concentrating on noise spectroscopy and another one concentrating on feedback control. So they're not actually advertised yet, but very, very soon. But if you're interested, come and talk to me or Gerardo. Okay, so back to my actual talk. So I'm going to begin with an introduction, as usual, and then talk about the difference between standard quantum limits and Heisenberg limits, because that's going to be crucial to the talk. Then I'm going to talk about three experiments, okay, even though I sort of basically only mentioned one in my title, but in a sense these two previous experiments, which were both also collaborations between me and the experimental group of Jeff Pryde, lead up to the final experiment, so I think it's natural to put it in context by also talking about them. So the first one was a multi-pass experiment. The second one was an experiment using entanglement. They both were using adaptive techniques, so this is where the control comes in. And then the last experiment combines all three of those, which I'll talk about. All right. So I'm going to, so it's some motivation. So we're talking about phase estimation. So probably everybody here knows that there are lots of good motivations for being interested in phase estimation, because all sorts of physical quantities can be correlated with phase, material properties, distances, displacements, forces, etc. Okay, so where quantum mechanics comes into generally into the field of estimation is that it puts limits on how well we can estimate things based on the quantum resources that we have. Okay? So in particular, the way I'm going to look at it is that when we're talking about the problem of estimating a phase, the fundamental resource, if you like, the fundamental thing that limits our ability to estimate an optical phase is the number of photon passes through that phase. Okay, so an important that this is photon passes, so it's not the number of photons and it's not the number of passes, it's the number of photon passes, and we'll see exactly how that works later. And so the ultimate quantum limit, or Heisenberg limit as it's become a convention to call it, scales for large n like pi over n squared, okay, for where n is the number of photon passes. And that's to be contrasted with the standard quantum limit, which scales just like 1 over n. Okay, so it's instead of n squared, it's just n, and so that's why people obviously would like to be able to reach this ultimate limit. Now, demonstrating something better than the standard quantum limit, that's been demonstrated many times, but what hasn't been demonstrated before is to obtain exactly the Heisenberg limit. So in other words, to get a mean square error, which is exactly as small, or essentially exactly as small, as what quantum mechanics allows. Right? So that has not been achieved until now, and so that's what I want to tell you about. Okay, so I'm going to present this a bit formally. So this is sort of a quantum information sort of language to describe what's going on here. To think of this, instead of talking about beams and optics, to think of this in terms of gates. Again, what we're really trying to estimate is a parameter in a gate. And so the gate is this particular gate called a phase gate, which looks like this. So basically, if the qubit is in state 1, then it gets a phase applied, a phi, and if it's in state 0, it doesn't. So we have this gate, okay? We also have access to, in the sense that we can implement it, right? We can also implement an auxiliary gate, which just for variety will make having the phase shift on state 0, but it really doesn't matter. Okay, and but the obvious way if we're actually interested in optical phase shift is that this photon, for example, could be a photon polarization qubit, okay, because there you get 2 states naturally. Another place you get 2 states naturally is a Mach-Zehnder interferometer because you have 2 arms. But anyway, where you get a differential phase shift between 2 different modes of a light field, either different polarization modes, different spatial modes, or whatever, can be thought of in this formalism. Okay. And so, yeah, so in the polarization case, which is actually the one used in all of the experiments I'll be talking about, then all of these gates are actually using a half-wave plate at the appropriate angle. Okay, so we have qubits, which we can put through these gates, and we're not, in principle, limited by the number of qubits. Okay, so this has been sitting down here all the bottom, right? We're not imposing any constraint on the number of qubits that we have. What we are counting, okay, so I'll get up to the one more point, right? Initially, we know nothing about this phase that we're estimating, okay? Now, you could say, well, that's not the case in a lot of problems I know about, and that could be very true. But I think the problem of phase estimation, if we're really thinking of this thing as a phase and not something else, then what we have to be able to deal with the fact of having a parameter that can be completely unknown in the whole range of values that a phase can take. Okay, so that's our starting point. So as I said, so the crucial thing that we are limited to is a number n of applications of that gate. Okay, so basically every time a qubit has that gate is applied to a qubit, that's an application of the gate, and that's the fundamental resource that is going to limit how well we can estimate this parameter phi. And what we are trying to do is to minimize the mean square error in our estimate, ultimately, or for technical reasons, rather than the mean square error, because it's a phase variable, mean square error is not a very well-defined thing. It can depend on the cut, the phase cut, for example. So what's nicer to use is a measure introduced by Halevo, which is defined in this way, which you look at it for half a minute and it still looks completely counterintuitive. But if you actually work this through for certain phase distributions, you can convince yourself that if it's a distribution with a small variance, then the number that you get out from this expression is the same as you'd get out from just a general, an ordinary mean square error calculation. Okay. Yes, okay, that's all I want to say about that. All right. So the standard quantum limit, so I've told you already how it scales, but what do we actually mean by standard quantum limit? What makes it standard? Well, it's just that we use a standard, the most straightforward, the most naive way we could think of measuring this parameter, okay? And that would be that if we're allowed to apply the gate n times, we just apply it on n separate qubits. So here's an example with 4 qubits. Down the bottom here. So we just independently prepare the qubits in a superposition state. Of course, it has to be a superposition of 0 and 1 because those states themselves are unchanged by the gate. So they each go through the gate. So that's what this u here means, or u to the 1. Okay, it's just applying that gate. And then in the end, we just measure it in the x basis. So that's what these measurements x are. And then on the basis of the results of these 4 output bits, we, in this case, for n equals 4, we can estimate what the phase is. Now, and as I told you already, that we can get a scaling of 1 over n independently of the true phase, but actually only if we use this auxiliary phase r. Okay, so that's what this thing here is. So this is this other phase shift. If we don't include something like that, then we end up being able to measure some phases more accurately than other phases. So here the role of this r is simply to give an extra rotation on each bit, so we're essentially equally sampling. So we're just rotating this by pi over n, and that's what we can achieve in this case. So here I've spread out where the measurement's taken, but of course there's no reason I couldn't collapse this entire thing and do them all in parallel. It really makes no difference, but I'm writing it out this way because as we go forwards, we'll see that it's actually important to spread them out this way. Okay, so that's the standard quantum limit. The Heisenberg limit is just when we say, well, we can do anything we like. The only thing we're limited to is applying this gate n times. And then, so if you just think about this problem, there's an obvious solution is to prepare n qubits in an entangled state, so to do a similar thing to what we did before, but now they're not in separable states, they're in this entangled state. Now this doesn't look like a qubit state, but what this means, so this S stands for symmetric, and so this is a symmetric state of n qubits, where I have a little n qubits in say the 1 state, and the rest of them in the 0 state. But that's symmetrized over all the arrangements that I can have. So that, of course, by itself is well, not a sort of interesting entangled state, but I take a superposition of those things as well, and I get an interesting entangled state. It turns out that the explicit expression I need to attain the Heisenberg limit for these coefficients is given by that. So that's the state which we need, and then the measurement we need is, well, or at least that we can do, is just a so-called canonical phase measurement. So that's something described by P of M involving these phase states, which are just equal superpositions over all of these types of symmetric number states which are introduced there. Okay, so a picture for that. So here's a picture for n equals 7. So I just have 7 qubits, so they could be initially all in state 0. I do some entangled state preparation. Then each of the qubit goes once through the gate, right? And then at the end I do this big entangled measurement. And as I said, in the asymptotic limit, this has a scaling in the mean square error which goes like pi squared over n squared. Okay, so this is a technique which you can see, like the previous one, I can do all of the gates in parallel, so that takes essentially no time. But what I could say about this scheme is that it's exponential in k. And have I said what k is here? Yes. So k is the number of significant digits in my estimate of the phase that I get at the end. Okay? So I can think of this as being an exponential scheme in terms of this parameter k, right? Exponential, if you like, in space, in terms of the number of qubits that I'm measuring, that I'm needing, is going to be exponential in that. So why? Yeah, so the reason it's exponential is that if I have a variance which goes like that, that means the standard deviation goes like 1 over n. So roughly the log of n is the number of. So if you think of it in a binary, that means I would have 2 to the minus k to equal the standard deviation. That's the last bit which has any information in it. What does k have to be? Well, k has to be of order log n. Right, okay, so that's why k is of order log n, and so n is of order e to the k. Okay, it's exponential in that sense. So there are alternative ways to also achieve the Heisenberg limit, which are not exponential in space in this way. And that's a so-called binary encoding scheme, okay, where I don't act the unitary or the gate only once on each qubit. I can act it more than once before I measure it, so in a coherent way. Right? So just to make the diagrams not become extremely long, instead of writing out u 4 times, I'm just going to write that as u to the 4, for example, here. So you think of this as actually 4 applications of the unitary gate u. So it turns out I can also achieve the Heisenberg limit in this way. So the number of qubits which I require here is now only of order k, okay? So it's linear, if you like, in k. But the price that I pay for that is that I'm now doing the number of applications of the unitary in a row, which I have to do, still is going to scale like n, so that becomes exponential now. So what I'm doing here is trading off the previous one, which was exponential in space, for a different scheme here, which is exponential in time. Okay, but it's still, as I said, actually gives me the standard quantum limit. It's just rearranging the way I'm using the resources. So I have here a different entangled state preparation. The unitary which I need. So in this case, the measurement which I need to do is well known quantum information. It's the so-called quantum phase estimation. Well, I should be a little bit more careful. But specifically, it's the quantum inverse Fourier quantum Fourier transform, followed by measurements in the logical basis. And those measurements directly give me a readout of the binary digits of my phase estimate. Okay, so that's what this notation here means. Okay, yeah, so this was something introduced by Shaw in 1994, as most people probably know. And yes, I think that's everything I've already said. Okay, so those are options for measuring the phase at the Heisenberg limit. Now, so if you give those two options to experimentalists, at least experimentalists in optics, like either do that or do that, they're going to say, well, I'd rather do something where I only need to entangle a few photons rather than a huge number of photons. So that's probably a good starting point. But then they'll also say, but do I really need to do this entangled state preparation? That sounds sort of hard. Could I get away with not doing that? And what about this entangling gate over here? That sounds sort of hard. Can I not have to do that? And anyway, so you think that through, and so it turns out that the second one of those, actually the answer is you do not have to do it at all. If all you're going to do after your quantum Fourier transform is measure your qubits, then as pointed out by Griffith and New in 1996, you can do that whole thing without any complicated unitary at all. You just need basically a feedback scheme or feed forward, depending on which way you look at it. So you have a state coming in here. Although you sort of have to, you have to mix the control and the unitaries, the phase unitaries which are applying like this. So essentially what you have to do is measure the qubit which underwent the most number of applications of the gate first, which could be a little counterintuitive. So you're measuring the least significant qubit, least significant bit of your phase first. Based on that result, then do a rotation on the remaining qubits, then do the one which has the next least significant, measure it, and etc. until you're done. Okay? So these, for those who aren't familiar, maybe I should have said, but the double lines here means that we're dealing with classical information. The single lines mean we're dealing with quantum information. And so after a measurement, you just have classical information. So this, while it looks like some sort of multi-qubit gate, it's not that. It's just that you've made a measurement, you have a classical result here. If you got the result 1, then you do these single qubit rotations. If you got the result 0, then you don't. Okay, so that's very easy to do experimentally. And you'll see that what's over here, I've replaced that, that entangled state input by just just like in the standard quantum limit, 3 independently prepared qubits. So, so this whole thing then is basically what is known as the quantum phase estimation algorithm. And it works in the sense that you can certainly get an estimate of a phase, and it can be an arbitrarily good estimate of the phase as you increase n the number of qubits that you're using, but it doesn't actually scale better than the standard quantum limit. In fact, it scales worse than the standard quantum limit. Okay, so you went through all of this work doing a relatively complicated thing, and you end up scaling worse than the standard quantum limit. Now, why is that? The quantum phase estimation is supposed to be a good, useful thing. So it turns out that it's because the distribution which you get has high wings. Okay, so it does actually have a narrow peak, as narrow as you would want for a Heisenberg limit, but it also has high wings, which which doesn't matter so much for quantum computing, but does matter if you're caring about a mean square error measure for your estimate of the phase. But also it suggests that it might be possible to fix this because a typical problem with high wings can be repeated just by repeating the thing over and over again. But we don't want to be quite that naive, just to exactly do the same thing over again. We want to do something like that, but in a bit of a sophisticated way. So, okay, so just to remind you, in the quantum phase estimation algorithm, the kth qubit passes through the unitary or the gate 2 to the k times. So what we generalize this to having, instead of 1 qubit passing through this 2 to the k times, we have m independently prepared qubits passing through this many times. And so the total number of resources that I'm using now, the total number of applications to the gate is multiplied by m. Okay, but the clever thing, so I haven't told you what the clever thing is that we don't just repeat the same experiment over and over again. We actually use, for every measurement which we're doing now, a locally optimal adaptive measurement. Okay, so Dominic Berry and I, a long time ago, introduced a general algorithm for doing this for phase measurements, and so we applied in this case. So it turns out in this case, for m equals 1, the locally optimal adaptive measurement scheme that we introduced becomes exactly the quantum phase estimation algorithm. Okay, whereas for m greater than 1, obviously it's something different, and it doesn't any longer realize an optimal phase measurement for m greater than 1. Nevertheless, we do find that as long as m is at least equal to 4, we get Heisenberg limited scaling. Okay? And for m equals 5, that turns out to give us the best scaling of about this. Okay, so it's a little bit of overhead compared to pi over n squared. It's 4.8 over n squared. But yeah, it's still the right scaling. Okay, so this is a picture of the experiment which we did back in 2007, which is published in Nature. And so it's just a single photon experiment with these multiple passes where we're controlling the number of passes which happen and also controlling where would it be? I guess it's, yeah, here we're controlling the phase that we're applying onto the qubit as well. So, and this is the results from that. So the standard quantum limit is asymptotic, is this line up here. So we scaled things or plotted things in the way that the standard quantum limit is a straight line versus n. Of course, it actually decreases with n, but we're multiplying by something, so it's a straight line. So we can clearly see the Heisenberg limit is something which goes below that, and that's what we've got here. So this is the ultimate limit, the Heisenberg limit with the ultimate coefficient that can be achieved. This is what the theory predicts, which is the same scaling, same 1 over n squared scaling, and these are the experimental points showing that, okay, until you get to quite a high number of passes, that we are tracking that very well. Okay, so that was the first experiment. Of course, people objected. Some people objected to the experiment and said, you know, but in my scheme, there's no way I could set up a multi-pass, and that's fair enough. There might be some situations where that's not something you could do. And for those situations, the only way you could surpass the standard quantum limit is to use entanglement. Okay, and so we did another experiment on going beyond the standard quantum limit by using entanglement. And so I want to talk about that. So I should make the point, a general comment about these experiments is that a lot of people have done phase estimation experiments without actually estimating an unknown phase. Okay, so typically they either start knowing basically what the phase is and just look for small deviations from it, or they just calculate a sensitivity, a hypothetical sensitivity to phase changes. So what's really different about these sets of experiments is where we are estimating a phase completely from scratch. We go in not knowing it at all, and we come out with a number, which is our phase estimate, and we work out what's the deviation of that from the true value that was set. Okay. So there have been lots of experiments with entanglement and phase, but this is what's special about this one. So we're basically using the same Barry-Wiseman locally optimal adaptive phase measurement, but now what we're going to apply it to is a sequence of entangled states going through the phase shift. So we don't have one giant entangled state. That would be optimal, but that's too hard to do. So we just have a sequence of smaller ones, which can be achieved. And in particular, what we have is basically one photon or two photon or four photon entangled states. And these are prepared by post-selection. So in other words, when we get the number of photons that we want, we count that as having achieved that bit of the experiment. Okay. So yes, but the particular states that were produced in this way are actually very easy to produce using spontaneous parametric down conversion, just by putting the outputs through a beam splitter. I'll show a picture in a minute. And so what we showed in this case was, for the first time, actually an ab initio estimation of the phase, right, from scratch, below the standard quantum limit. Okay, and without using multiple passes, using entanglement instead. And also, in principle, the technique we used, if we were able to scale it up, not just to have 1 and 2 and 4 photon states, but to be able to continue to go up to 8, 16, etc. If we were able to do that with perfect states, then we could also obtain Heisenberg limit scaling with this scheme, but we didn't go beyond the 4 photon level. And so this was published in Nature Photonics in 2011. So here's a picture of the experiment. I think I probably won't go through it, just to point out that the main thing about it, so preparing the entangled states is the very easy thing which is happening over here. The outputs from the down converter get combined on a beam splitter, and that produces the entanglement. Most of the complication is just having all of these lots of detectors over here, because we're producing full photon states, so there are lots of different ways, lots of different patterns that you can get for detecting those, and we need detectors to cover them all to be able to estimate the phase in a single shot. Okay, and so these are the results from that experiment. So again, the straight line, which is not actually plotted, but would be here at 1, is the standard quantum limit. So here the total number is much smaller, and so in this case, because it's all single pass, then resources is actually the number of photons detected. And the Heisenberg limit is going down here like this, and these are our results. So you see that they're not scaling at the Heisenberg limit because we were limited to 4 photons, okay? So you can actually work out what our limit is because of their 4 photons. We're getting down towards that. But if we had no limit on the number, we could have got, in principle, we could get something which was scaling at the Heisenberg limit, but not actually with the same coefficient again. Okay, so on to the last experiment now, which you can see, as I said before, is combining multi-passes and entanglement. So the motivation for this is, okay, we've seen that using adaptive measurements, which were used in both of those previous experiments, we were able to measure Heisenberg limit scaling, but not the exact Heisenberg limit, by using multiple passes of unentangled qubits. So that was an exponential in time type of approach, right? Small number of qubits, many passes, right? Or by using just single passes of entangled qubits, so this would be an exponential in space approach, we could in principle get Heisenberg leaving the scaling, but not at the exact Heisenberg limit again. So you might wonder, well, what if I combine all of those things, right? What if I combine the adaptive measurements and multiple passes and entanglement to get a scheme which looks something like this, okay? So I'm doing the, this is my quantum Fourier transform, if you like, which I know is the optimal measurement to do, but instead of just putting in single photons, what if I prepare an entangled state over here? Can we attain the exact Heisenberg limit for the first time? Well, you know obviously the answer. I wouldn't put up a question if the answer wasn't yes. So in some sense, right, with some caveats, which we'll get to. So to begin with, here's the, this is the state preparation part of the experiment. So it's not with very many photons, okay, and it's not with very many resources. So this is actually a 2-photon n equals 3 experiment, okay? So I'm going to, so it's not even with this big. It's actually just 2 coming in here, and so yeah, it's really just the top part of this this picture here, and I'll talk a bit more about why that is later. So k equals 2, the number of bits that I get out in my phase estimate is only going to be 2, and the number of resources I use is 3. Okay, so one photon is going to go through the phase shift twice, and the other photon is going to go through it once. And right, okay, so using the optics language of H and V now, horizontal and vertical polarization for my 0 and 1 state, the state that I want to prepare is a state that looks like this, okay, which is a somewhat complicated entangled state. So these coefficients are alpha 0 and alpha 1. They're the ones that were defined way back on slide number 5 or something like that. Okay, so this is relatively easy to make using spontaneous parametric down conversion. Not quite as simple as just putting the outputs on a beam splitter. We actually have to do an interesting logic gate, and one of the things about that is it's actually a non-deterministic C0 gate. So this is part of the caveats. So not only in this experiment are we post-selecting on getting clicks and seeing photons in the first place, we're also post-selecting on getting clicks in the right place so that we know we've actually produced this entangling gate so as to produce the state that we want. But anyway, but this is the state that we're trying to produce. So this is a tomography plot, or the elements of the density matrix. You see they're all supposed to be real. And as I said, it's relatively easy to make it because there's very little difference between theory and experiment here. And in fact, I tricked you because this was actually the experiment and this is the theory. Okay. Well, hopefully I tricked some of you. Anyway, the point is that right, we can say this is, well, rather this is what we want, and we're able to actually produce that to very high fidelity. Okay, then what do we do with that state is send it to, as I said, one of the photon. So I can imagine that this state is being prepared at this point. Okay, that's a little bit misleading because we only know that the state is being prepared after we get the right pattern of clicks, which is to say a photon detection in this apparatus and another one in this one. But if we get that, we know we prepared the right state at this point here. And then one of these photons goes through the phase shift, which is this great big thing here. This is the unitary gate, if you like. One it goes through, comes back and goes through a second time and gets detected, whereas the first one goes through here. Okay, so the other thing in this apparatus to look at, so this is the adaptive, in quotes, halfway plate or another phase shift. So to do this completely, to do this really rigorously, what we would have to do is, if you remember, we want to detect the photon which went through the phase shift twice first, and then on the basis of that click, change the setting for that wave plate there. That's difficult, apparently too difficult, at least for this experiment, because it would mean you would have to put this photon in a very long delay line and wait until you actually got the electronics and did the switching there before putting it through and detecting it. So again, caveat that where we want to think of this as an adaptive scheme, we're actually, if you like, post-selecting on we just set this one way or the other way, and we look at the data for the cases where it was actually set the right way, given the click which we got over here. Okay, so with that caveat, this is the data which we got. So what we're plotting here is, so this is the probability of the 4 possible clicks. So basically, the photon can be in, really, I should have 2 photon detectors here, and I can talk about it being one or the other, but they actually got switched around. But anyway, so I've got 4 possible outcomes, 2 photons, 4 possible outcomes, and this is the probability for each of those outcomes as a function of the true phase. Okay, and so the hard thing, you know, say, well, what do I take away from that? The important thing that's really hard to do, like why we had to work so hard to get that entangled state, is that these wings here are extremely small. Okay, so we've got quite broad peaks, as you see, but they have really small wings, which means that the probability of getting a completely wrong estimate is very small. And so that's what we get. So then this is the actual data. So this is a complicated plot, I know. This is the Halevo phase variance, which you can think of as roughly the mean square error as a function of the actual applied phase phi down here. For the standard quantum limit, we have this green theory. So that's the ultimate limit, and then the dashed line is what we'd expect from our experiment given its imperfections, and the brown data points are what we saw. Okay, so that all matches pretty well. The interesting things, the curvy ones, this comes from our entangled state, and so again, so the blue is if everything were perfect, I think, or is it? Yes, I think that's right. I think it is. And the red is the data points. So you see they match pretty well. They're a little bit higher than they should be down here at the minima, but it still matches fairly well. And if I do the appropriate average of what I want, then what I get is this dashed red line here. Okay, so that's just an average. It's not fitting to anything. Okay, that's just taking all these points and plotting it on this graph. But the important point is that it's barely above this blue line here, which is the theoretical Heisenberg limit for this number of resources, 3 resources. So we get essentially down to the Heisenberg limit is what we're seeing there. Okay, so you could ask the question, is all of this work actually necessary? Was it necessary to use adaptive measurement and entanglement and multi-passes to get to this Heisenberg limit for this case? Well, we can say yes, in the sense that we calculated, and some of these results had already been calculated, what if we have, so the experiment which we've got here is combining entanglement, and so I'm making an assumption that it's a symmetric entanglement, which it is for all the states I've talked about so far. So we have entanglement, multipass, and adaptive measurements. This is achieving the exact Heisenberg limit, and then this is what we saw experimentally. Okay. If I throw away any one of these, so if I take out the multipasses, or I take out the entanglement, or I take out the adaptive measurements, then I can't achieve the Heisenberg limit anymore, and also I actually get a value which is significantly higher than what was achieved in the experiment. Okay, so significantly higher in the sense that the experimental error in this number means that there are many standard deviations between this and that. So not only did we beat the standard quantum limit, which is all the way up here, right, of having none of these interesting things happening, but we also beat any of the 2 out of 3 schemes. Okay, by around about 10 standard deviation. Okay, so to conclude, okay, so Heisenberg limit is given that I have n possible applications of a gate to an indefinite number of qubits, scales like pi over n squared. Prior to the experiment which I've just talked about, the best that had been achieved was to demonstrate Heisenberg limited scaling. That's to say a variance which is proportional to 1 over n squared for large n, but doesn't achieve the exact coefficient. And what we've done in this experiment is to attain within 5% the exact Heisenberg limit for a particular very small number of n, by combining for the first time all 3 of these strategies of preparation of a symmetric entangled state of order this many qubits, multiple passes through the gate of any chosen qubit, and then control of individual qubits based on the prior result. So that's the adaptive measurement part. And as I was just saying, so our results not only get very close to the Heisenberg limit, they convincingly undercut the best that's theoretically possible. Okay, so for a perfect experiment with any two out of these three, we've done better than that with the experiment which we've done here. Okay, thank you.
Thank you, Howard. So, is there any questions? We have time for some questions.
Is it possible to apply this type of strategy to real, say, to real measurement?
Real measurement. Well, I will say that certainly the multi-pass technique, which you can just think of as being coherently applying a gate a certain number of times in a clever way, that's been applied in, I think it was experiments with NV qubits for measuring magnetic fields. Now, I don't know whether that counts as real, but that's certainly been applied. Now, they didn't produce an entangled state for doing that, but if they had, then they could, then they could do even better. I'm not sure how realistic it is to produce that, but I think there is there would be the possibility of doing that. Of course, it's the amount that you gain by using entanglement in this case is only a factor of 2, or don't know exactly what the factor is. So it would depend on how easy it is in your system to actually create entanglement, whether or not it would be a useful thing to do. But in principle, yes.
In metrology for atomic clocks?
Right. So I mean, this is a question people always ask about atomic clocks. I mean, it's a very good question. I mean, in a sense, essentially they're already working, I think, at the limit where the number of applications of the gate is essentially set by the decoherence of the atom. So what they're really limited by is, so in a sense, I mean, it's sort of a very obvious thing, right? That it's better if you're trying to measure a parameter very accurately, it's better instead of just rotating once, but rather if you know roughly where it is, you rotate it many times, and that's a fairly intuitive thing. So with the atomic clocks, they're not usually they're not in the scenario of starting with something completely unknown. They usually, they have a very good idea, and then the longer they do experiments, the better and better the idea they have, until you get to the point where the number of cycles you can apply is limited by the lifetime of your atom. So I think that it's in a different regime in a sense, because they're not really, they're not limited by, I suppose you could look at it in the sense that they are limited by the resources time, but that time is set by the lifetime of the atom. So you could sort of say that you could relate it in that way, but I guess it's harder to draw an exact analogy, because they're as I said, they're not starting from the situation of estimating a parameter ab initio. Okay.
Any other questions? Yes.
Okay, so yes. So my question is whether the scams are possible to extend to multi-parameter estimation.
Multi-parameter estimation. Yeah, that's also a good question. Certainly, be a lot harder. So yeah, it's not something we've looked at. I mean, there has been work done. Maybe even you've been involved. I'm not sure, but people have looked at the problem of adaptive multi-parameter estimation, for example, and typically, Yeah, typically it works much better if you know one parameter better than the other parameters. So what can make sense is to concentrate for a while on estimating one parameter, then once you know that well, you can treat it as effectively fixed, and then concentrating on measuring the other parameter by an adaptive technique and maybe alternate like that. That's probably not the absolutely optimal thing to do. But certainly adaptive measurement certainly makes sense in multi-parameter estimation. I'm not sure about the other things about entanglement and multi-passes, whether that makes sense or not. Yeah.
Oh, is there any other questions? Or, yeah.
Yes, so you insisted on the fact that it's ab initio estimation.
Yeah.
So how does the situation change if we have some information about the initial phase?
Yeah. So we've done some theoretical work on how things change. If you're really talking about asymptotic, I mean, there's some interesting things that come out. I mean, if you're really talking about asymptotic scaling with n, for example, like, so a lot of people will make the claim that well, the best states to prepare for estimation are noon states. But in fact, if you're talking about large n, okay, for any initial uncertainty, asymptotically a noon state will give you one bit of information per measurement. So noon states are actually, you know, in the asymptotic limit of large n, are completely useless for phase estimation if there is any finite uncertainty initially. And that's simply because in the limit of large n, the oscillations in the noon state are you're always going to end up with multiple oscillations in your region of uncertainty if you have any finite amount of uncertainty. So some of the statements which come out from thinking about the ab initio case still do apply in the case of uncertainty which doesn't cover the full 0 to 2 pi range, and those are things including the fact that, yeah, the noon states are actually not useful on their own for phase estimation if you have any uncertainty in the phase, and you want to actually, if you wanted to actually prove Heisenberg limited scaling or achieve Heisenberg limited scaling. So yeah, there are a number. You have to be careful, I think. I mean, I wouldn't say there's any simple answer, but you certainly have to be careful with designing schemes which seem optimal if you know the phase, and then assuming that they will still be optimal even if there's a small amount of uncertainty, because you can just get the wrong answer doing that. So there's a comment at least.
Perhaps the last question, if there is one. Yes, so it seems that there is no more questions.
Okay.